In this video, we're going to continue talking about limits. So this is the start of learning target 1B, which is entitled Limits, Limits, and More Limits. So in our last video, we talked about some methods for computing limits that were direct substitution, factoring, using a conjugate, finding a common denominator, or how to use the algebraic definition of an absolute value to look at both the left and the right side of that limit and then deal with computing the overall limit. In this video, we're going to only talk about one type of limit. We're going to focus in on some what we call special trig limits. So down below here, I have two special trig limits for us, and in this video, we're going to just focus in on the first one right now, which says that the limit as x approaches 0 of sine of x over x is equal to 1. Well, if I do a direct substitution, we end up getting an indeterminate form. So if I sub in 0 directly, I get sine of 0 over 0. Sine of 0 is 0, so I would end up with the 0 over 0 indeterminate form. So you might be wondering, well, why the heck then is this limit going to be equal to 1? Well, what I want us to look at is this from a graph perspective. So on our graph perspective here, let me slide this over. I have graphed sine of x over x. We can see that that is our first function, our f1 of x up here. Sine of x over x, and we get this kind of sine wave as it's going through. If we look at this, we can see that the left and the right, it appears that they are both approaching a value. And if we look at these tick marks, each tick mark is 0.2, so we are technically up at 1, but let's really see what's happening from the left and the right side. So I have a table over here, and I'm going to start with the value of negative 0.05. So it's really, really close on the left-hand side. It's already at 0.999583. And as I go up and I continue approaching from the left-hand side and I get closer and closer, we keep getting values that keep approaching 1, 0.999933, 0.999983. I'm definitely getting closer as I get down to 0.01. So if I keep going, well, it actually tells me at 0 that this value is undefined. And it is because I have this indeterminate form. But what we're looking at is not the function value at that point, but the limit. So I'm looking at what's happening as I approach in from the left. So right here, these values are telling me that as I approach in from the left-hand side, I'm getting really, really close to 1. I can see that on the graph as this comes in. As I approach in, I'm getting really, really close to 1 up here. And if I look at this from the flip side, if I start at values that are bigger than 1 now, and I approach in from the right, I can say I'm at 0.99985, then I get to 0.999933, and I get even closer at 0.99983. So as I approach in from the right-hand side as well, those are both approaching the same value, which is going to be 1. So using a graph perspective from here, although we don't have a way to manipulate that limit yet, we will have to talk about it later in this course, but for right now, as we approach and we use a graph perspective on both of these, we can see that although that function is undefined at x equals 0, we still do get a limit since the left and the right side are both equal to each other, and as they approach from both sides, we're approaching a y value of 1 then. Well, this is actually true anytime the stuff inside the sine value is divided by the same thing. So, over here, I have kind of this alternative perspective of the limit as x approaches 0 of sine of smiley face over smiley face is equal to 1. And what this is representing is that as long as my input on my sine function is the same as what my denominator is, I can always say that this limit is going to be equal to 1. So we are going to do some algebraic manipulation, you could say, to be able to take advantage of using this limit. Likewise, because 1 is also its reciprocal of 1, if I flip-flop these, I would technically be getting 1 over 1, which is also going to be equal to 1 as well. And the second limit down here we're going to talk about in class together. So let's look at this first example. It says evaluate the following limits. It says the limit as x approaches 0 of sine of 2x all over x. So right now I have something that looks similar to what I'm given. I have a 2x, but I have just an x in the denominator. My goal is that whatever is inside my sine function, I want to be dividing by that as well. Now, what I'm allowed to do and what I'm not allowed to do, we have to be very careful of. I am not allowed to manipulate what's inside the sine function. There is no way to change that. That 2x is stuck. What I am allowed to manipulate is multiplying by that fancy number 1 that we talked about in our last video. So my goal right here is going to be to multiply by a fancy number 1 however many times I need to get this limit to work out. What I'm missing here is that technically I would want a 2 down here in the denominator, because that way my input of 2x, so I have sine of 2x all over that exact same 2x. But it's not fair to just divide by 2x, that's changing the problem. But what I can do is also multiply by 2. So technically here I'm multiplying by 2 and dividing by 2, so I'm technically just multiplying by our fancy number 1. And when I do that, then I can actually evaluate this limit. So this first part of this limit is going to 1. Using the same, if we were to go back to our graph and graph this same function, we would see a similar graph as it approaches to 1. And we know that the limit of a constant is unaffected, so I get 1 times 2. So I end up getting 2 for this answer for this limit then. I don't write the limit as x approaches 0 in front of it, since I'm actually taking the limit by saying that that limit value is equal to 1. And we were again allowed to do this because what I'm technically doing is multiplying by 2 and dividing by 2. So I'm multiplying by our fancy number 1, which does not change the problem at all. Let's look at example 2. So in example 2, it says the limit as x approaches 0 of sine of 3x all over 10x. Now remember, what am I allowed to change and what am I not allowed to change? I am not allowed to change this 3x. That sine of 3x is stuck. There's no way I can take things in and out of trig functions. That is not valid mathematics. But what I can manipulate is the stuff that is in the denominator in this case. My goal would be to have a 3 here instead of this 10. Well, the 10 isn't really in the way. It's just kind of extra information. So what I'm going to do is I'm going to rewrite this problem and I'm going to move the 10 all the way over here. I'm going to just take it out of the way. So I have sine of 3x all over x times, technically I guess, 1 over 10. All I've done is just rewritten the problem and kind of group the stuff together that I'm interested in and move the extra constants or extra coefficients over to the side. Now this is still part of the limit. It doesn't completely go away. I'm just kind of moving it to the side so I can focus in on this sine piece. What I would want to happen on this sine piece is I would want a 3x down here, because that way the inside of the sine function matches what it's divided by. But again, I can't just divide by 3, that would be changing the problem. But what I can do to counterbalance that is also multiply by 3, so that I'm technically multiplying by 3 over 3, which is equal to the number 1. This is how I can algebraically manipulate it, because I technically haven't changed the problem. The problem is still, technically, if I reduce it back down, I still get sine of 3x over 10x. But I've kind of strategically rewritten this so that I have a part of this right here that allows me to use my special trig limit. So by evaluating the limit as x approaches 0 of sine of 3x over 3x, well, that's going to be equal to 1, times the limit as x approaches 0 of 1 over 10 and 3 are not affected. So I get 1 times 1/10 times 3, and I end up with 3/10 then as my final answer. Let's look at some more examples. So in example 3 here, it says the limit as x approaches 0 of 5x over sine of x. Now this did flip and my sine did go to the denominator, but just like before, I mentioned this at the beginning, that technically this will also work if I have the limit as x approaches 0 of smiley face, let's say, over sine of smiley face. That would technically be equal to 1 over 1, but 1 over 1 will give us 1. So it's okay if I kind of flip-flop where our sine function is. So on this example, think about what you can change and what you cannot change. So I cannot change the inside part of my sine. So sine of x is stuck. But what I can do is kind of move the 5 to the side. I don't need it for this limit. So I have the limit as x approaches 0 of x over sine of x times 5. Now from here, this x over sine of x limit, that is going to be equal to 1. It's exactly matching up to the original limit, it's just the reciprocal of it. So if I'm being precise, I guess I could say it's 1 over 1 times that 5 that I had that was kind of a scalar or a coefficient on this problem, and I end up with 5 then as my final answer. So we can see through these first 3 examples how we can algebraically manipulate by kind of moving scalars to the side, how we move the 5 and the 1/10, and then multiplying in by our fancy number 1s if I needed to, like in examples 1 and example 2. Let's look at example 4. So in example 4, I have the limit as x approaches 0 of tangent of 2x over x. Now one thing I didn't address with the first 3 examples was technically I should have been trying direct substitution. But if I look at all 3 of these, the first problem has an x in the denominator. So if I sub in 0, I'm going to have a 0. Same thing on the second problem. And likewise on the third problem, if I sub in 0, sine of 0 is going to be equal to 0. So that does not work out. So in case we need a little refresher on trig here, sine of 0 is going to be equal to 0. Well, if we look at example 4, I have a tangent of 2x over an x. Well, if I sub in 0, I'm dividing by 0 as well. That's giving me a problem. But my special trig limit had nothing to do with tangent. It talked about sine. Any ideas for how we could start to kind of rewrite this or manipulate this? Well, we can use what the definition of tangent is. Tangent is actually defined to be sine over cosine. So I can rewrite this as the limit as x approaches 0 of, instead of tangent of 2x, it'd be sine of 2x over cosine of 2x all over that original x that we had. Now, fractions over fractions are very messy, so I'm going to go ahead and multiply by the reciprocal. So I get the limit as x approaches 0 of sine of 2x all over cosine of 2x times the reciprocal of x will be 1 over x. So I haven't done any calculus yet. All I've done is reuse the definition of tangent to rewrite the problem and then kind of reduced it down so I don't have multiple fractions here. The next thing I want to use is I want to think about my limit. Well, if I do a direct substitution, I still have this issue of dividing by 0 since I still have an x in the denominator. So what I want to use instead is that special trig limit, and I kind of want to regroup things. So I know that the sine of the 2x needs a 2x in the denominator if I'm going to use that limit. So I'm going to start to rewrite this. We have the limit as x approaches 0, sine of 2x over, now I'm going to put this over the x here and flip-flop where the x and the cosine are. And I can do that because multiplication is commutative and cosine of 2x and x are both in the denominator. And so instead, I'm going to multiply by 1 over cosine of 2x. Now, if I think about this, I'm going to ignore the cosine for a second and just focus in on the sine of 2x over x. What would I need to do here so that I can apply my special trig limit? Well, what I would need is I would need a 2 in the denominator down here so that the 2x also has a matching 2x in the denominator because the stuff inside the sign can't change. But it wouldn't be fair to just divide by 2. I also have to multiply by a 2 to keep this equation balanced. Now, when I do that, the first piece is taken care of. Sine of the limit as x approaches 0 of sine of 2x over 2x is going to be equal to 1. The 2 over here that I am multiplying by is also going to be fine because it's a constant, but I have to think about the cosine. If I substitute in a 0 here, what is cosine of 0 equal to? Well, cosine of 0 is equal to 1, so it's okay if I divide by 1. I haven't changed anything there. So when I take this limit now, this first piece is going to 1. I get times 1 over cosine of 0 times the 2. We just said that cosine of 0 is equal to 1, so I get 1 times 2, and I end up with 2 as my final answer then. So remembering all of those exact value facts from trig is important, and we want to have that stuff readily available as we're going through these problems so we are seeing different tricks and tips quicker as we go through these. So if we need a refresher on the unit circle, might be a great time to take that. Okay, let's look at example 5. So example 5 says the limit as x approaches 0 of 5x over tangent of 7x. Why don't you guys pause the video and try example 5 on your own first, and then we'll check it together. Let's check example 5. So it looks very similar to 4. I just have flip-flopped where the tangent and where the x is. I'm going to go ahead and use the definition of tangent right away, because if I try to direct substitution, I have 0 on the top, which could be okay, but in the denominator I also have 0, because tangent of 0 is equal to 0 as well, so this is an indeterminate form. So when I go to manipulate this, I still have a 5x in the numerator. Tangent of 7x can be rewritten as sine of 7x over cosine of 7x. Make sure that they are both a 7x, since they're coming from the tangent. The inputs on both the sine and the cosine must be the same. From here, I'm going to multiply by the reciprocal of the denominator so that I don't have multiple fractions, I just have one, and I end up with the limit as x approaches 0 of 5x times cosine of 7x. That was a 7, all over sine of 7x. Now from here, I want to play this kind of rearranging game. So the cosine is not the issue. The cosine is not going to cause me any problems, it's the sine. Because if I sub in 0, sine of 0 is unfortunately 0, and I cannot divide through by 0. So what I'm going to do is I'm going to group these together. The sine of 7x would want the x, it's not going to want the 5 though. It's instead going to want a 7, which I'm going to have to figure out how to add that in there. So I still have a limit, since I have not actually done any calculus yet. So I have the limit as x approaches 0 of x over sine of 7x times this 5 cosine of 7x is off on its own over here to the left. What's missing for this first piece is I need a 7 in the numerator, but I can't just multiply by 7. I also need to divide through by 7 so that those are counterbalancing each other, and I'm technically multiplying by the number 1, or our fancy version of the number 1 here, since I have 7 over 7. Now from here, the reason I wanted to do that is because the limit then, as x approaches 0 of 7x over sine of 7x, this will go to 1. And then on the second guy, I'll get 5 times cosine of 0 by directly subbing in, all over 7. Now I'm writing this a little backwards here. Cosine of 0 is 1, and I end up with 5 over 7 as my final answer then. So we can see, using kind of all of our tricks that we had from Trig, we can work through some of these problems. Let's look at example 6. Why don't you guys pause the video and try example 6 on your own first, and then we will check it together. So let's look at example 6. It says the limit as x approaches 0 of tangent of 2x over cosine of 2x. Well, I don't have any sines. I could rewrite tangent to be sine over cosine and manipulate it from there, but really the first thing I should always be trying is, can I do a direct substitution? Well, let's see. If I directly sub in, I get tangent of 0 over cosine of 0. Well, this will actually work out, because cosine of 0 is equal to 1, tangent of 0 is equal to 0, 0 divided by 1 is okay, and I end up with 0. So don't let these fool you. Some of these can still be direct substitution, so we want to keep that in the back of our mind, because it'd be a quicker way to finish off the limit problem. Now, if you solved example 6 similar to how we did 4 and 5, that will actually work out as well. It's just going to take you a little bit longer to get there. So think about all the different methods you have and different ways that you can approach these. Okay, let's look at example 7. We have a cosecant now. So we have the limit as x approaches 0 of x times cosecant of 3x all over cosine of 5x. Okay, well, I have a cosine in the denominator again, so maybe direct substitution will work. If I directly sub this in, let's see what happens. I get 0 times cosecant of 0, well, we're going to have to figure out what cosecant of 0 is, over cosine of 0. we know cosine of 0 is okay. That's going to be equal to 1. But in the numerator here, cosecant, as a little refresher, I'm going to stick it over here, cosecant of x is equal to 1 over sine of x. So what that means then is that I have 0 times 1 over sine of 0. Oops. But sine of 0 is equal to 0, and this is giving me a problem because I ended up with technically 0 over 0 all over 1. So I still do get this indeterminate form here, and I have to worry about that. So unfortunately, direct substitution in this case will not work. So let's try another route. The next route would be, well, let's go straight to the definition of cosecant, and let's start remanipulating these in terms of sine and cosine. So I have the limit as x approaches 0 of x times 1 over sine of 3x all over cosine of 5x. From here, if I want to get rid of all these fractions, we have the limit as x approaches 0. We have x over sine in the numerator all over cosine of 5x in the denominator. So from here, if I want to get rid of all those fractions, we have the limit as x approaches 0 of x over sine of 3x times technically 1 over cosine of 5x. Well, that looks a lot nicer in what we're used to. Let me rewrite that x. So we had the x over sine of 3x times 1 over cosine of 5x. Well, this looks really close to what we're used to being able to manipulate. What's missing here is this sine needs that 3 in the numerator, so it matches with the 3x. But I can't just multiply by 3. I also need to divide by 3 then. So I'm really multiplying by 3 over 3, which is our fancy number 1. From here, we know that this first limit is going to 1, since I have the limit as x approaches 0 of 3x over sine of 3x times 1 over cosine of 0, which I can directly sub in, times 1/3. The last step from here, cosine of 0, we know is equal to 1. So I end up with 1 times 1 over 1 times 1/3. So I end up with 1/3 then as our final answer. So even if it gets a little messier and we're seeing other trig functions, if a direct substitution doesn't work right away, a good trick would be convert everything to sine and cosines, kind of regroup stuff together, get rid of all those fractions within fractions, and then kind of reevaluate and see what you're left with. So although the beginning portion of 7 looked messy with the cosecant, once I rewrote it in terms of sine and cosine and got down here to this step where I'm going to put the star right here, we could see how this is similar to other things that we have done. Let's look at 2 more examples. So example 8 says the limit as x approaches 0 of sine of x over x squared minus x. Why don't you guys pause the video and think about how we could approach example 8. So in example 8, if I try to do a direct sub, I'm going to end up with 0 over 0. So a direct sub will not work in this case, but what I can think about doing is, well, everything's in terms of sine and cosine, well, just in terms of sine, but this x squared minus x, I can actually factor, and I can rewrite this as the limit as x approaches 0 of sine of x over x squared minus x would become an x times an x minus 1 by factoring out the greatest common factor. From here, this looks really similar to what I wanted. I'm going to actually break it apart so I can group stuff together that's helpful. So I'll have the sine of x over just the single x times this 1 over x minus 1 off to the side. Well, from here, sine of x over x, that limit as x approaches 0 is equal to 1 times, I can directly sub in on the second piece, and I get 1 over 0 minus 1. So I end up with -1 then as my final answer. Why don't you guys pause the video and try example 9 on your own first. Okay, let's check example 9. So example 9 says the limit as x approaches 0 of sine of 9x over x squared minus 2x. So this is going to be a similar trick. If I try to do a direct sub, I end up with 0 over 0, and that's not going to work out. So instead, I'm going to factor that denominator. Since I have a quadratic, I can factor it as x times x minus 2 in this case. Then I have a sine of 9x in the numerator. From here, I'm going to kind of put the stuff together that might be my special trig limit. So sine of 9x over the x, and move the 1 over x minus 2 just to the side. It's still part of the problem. They were being multiplied here when I factored, so they're still being multiplied. I haven't changed anything. But what I do need to manipulate from here is that this 9x can't change, so I need a 9 down here. But to counterbalance that, I have to multiply by a 9 as well. So I'm technically just multiplying by our fancy number 1. What this allows me to do from here is that this first limit as x approaches 0 of sine of 9x over 9x, that's going to be equal to 1 times I can directly substitute in on our second one, since 0 minus 2 will give me a non-zero number. So I end up with negative 9 over 2 when I simplify all of that down. So we've seen quite a variety of examples as we've gone through these first 9 examples here. And when in doubt, try direct substitution right away. If that works, like it did on example 6, then we're good to go. If it doesn't, try converting to sines and cosines and using that special trig limit. And maybe if you see a quadratic in here, like on examples 8 and 9, we might need to do some factoring.